Perfect. So I'm the first one. I think someone has tried it already the wrong way. Okay, okay.
Funciona? Sim? Okay. So, thank you everyone for coming to our first seminar of probability in stochastic process from 2022. And this is our very first seminar on this new protocol when we have some people in the audience, and we are also live on YouTube. So open this new way of doing our seminars. We have today with us Professor Gunter Schütz.
Yes.
And if you are on YouTube and you have questions to Professor, you can send the questions on chat, and I will pass your questions to Professor. So thank you very much for accepting the invitation, and the blackboard is yours.
Okay, thank you very much for the invitation from my side. It's a great pleasure to be here again. Unfortunately, it's a short visit this time, with just a few occasions to come here, but anyway, I'm happy to be here now. So I'm going to talk about something that I've read there, integrability, supersymmetry, and duality for a system of interacting particles, which I call vicious Walker's web with pair equation. I'll explain why I call it like this. This is joint work that I started with Vladimir some 2 years ago, or 2 or 3 years ago by now, and with a follow-up with Dragi Karevsky from the University of Lorraine that was just published a short while ago. So, okay, I will begin first with some definitions, explain the model and the question, and there will be a lot of notation that you might not be used to, so I will introduce it so that you can follow the results. Then I will present time to for the results, and then just make some remarks on the proofs. They are quite technical, so I'm not sure it makes too much sense to go into great detail, but anyway, I will go through it to give you some idea of how we go about this problem. Okay, so first of all, let me talk the basic settings. So we have an interacting particle system in one dimension. So we have a lattice of L sides, which can be either a torus, so it can be periodic boundary conditions, or it can be just a finite box where you have sides which account from 1 to L and no jump or anything between 1 and L. So it's just like a box with a fixed boundary, or a torus, a ring, where you don't have a beginning and an end. So this is the two types of lattices I will discuss. And then I will have, well, each lattice side will be either empty or occupied by one particle. So I will have particles that somehow jump on this lattice, but you can never have more than 2 particles on a side. So these the occupation particles I will just call eta k. This is 0 or 1, and then the whole configuration is just this collection of occupation variables, which I call just eta without any subscript. Or alternatively, I denote the configuration by the set of occupied sites. So if you see an eta, this will be a set of occupation numbers 0 or 1, and if you see a bold-faced letter, this will be just a subset of this torus, namely those particles which have eta k equal to 1, which are occupied. Both representation of the state space is useful. Okay, now, as I say, this is a configuration, but of course I have processes that can change this configuration. So one change is a flip. So from 0 I go to 1 and vice versa, and the other one is just double flip, where you exchange 0 0 to 1 1, 1 0 to 0 1, and so on. So you just flip both occupation variables on neighboring sides. So you start with the configuration eta, and then you have this configuration eta here, which is defined in terms of original occupation variables as follows. So now this is just what I will use, and now here's my process. What can happen? And then you will see why these notations are meaningful. So first of all, as I say, I have particles on this lattice, and what can happen is that either particle jump between nearest neighbor sites. Okay, so we can jump from 0, particle can jump to its right or left nearest neighbor, and this jump will be symmetric, and it has a rate w. It's a Markov process. Then I can have a deposition of two particles. So let's say I have two sites. Let's say there's nothing. I can just add two particles, okay? But not on the same site or neighboring sites. And finally, if somehow I get two particles on the same site, either by a jump or by a deposition, so imagine I have already 5 sites on one of them and I add a pair, then I would have 6, but it doesn't happen. As soon as I get 2, I annihilate immediately, okay? So the result of this immediate annihilation is the following. You will never have more than one particle per site. Because just imagine you start with only 1 and zeros. Okay, you can generate 2 by a jump on occupied site, but they will immediately go away. So there will never be 2 particles. And the same if I deposit a pair. Let's say I deposit on 1 0. Then here I would get 1, that's okay. But here I will get 0, I will get 2, which is immediately annihilated into 0. So in actual fact, a deposition of 1 0 will be the same as a jump from 1 0 to 0 1. In the final result. Okay, so this is my process. That's why in the end I can work with just the local state space of zeros and ones in this process. So that's what I try to explain here. So these are my original rates, but you can just as well say, okay, I have a process with just these transitions and the transition 1 1 to 0 0, but then with a rate that's a bit different, namely here in this case, for instance, to illustrate what can happen. How can I go from here to here? Well, I can go from 1 1 to 0 0 in this terminology by jumping from this to here. I will get 2 immediately goes to 0, so I end up with 0 0. It can happen with the right jump from here to here, right, from right to left. I will end up with 0 0 because of this process, or by a deposition of 1 1 onto this pair of sites will also end up here. So this transition will in the end have a rate 2w plus mu. Okay, but these are equivalent descriptions of the process. Because I can also have a deposition with rate mu that leads to yeah, true, but I create on this one, right? So I would get 2 2, but both annihilate immediately. So even though I create 2 particles, I actually annihilate. No, you can create anywhere, right? Yes, exactly, any 2. This was just for illustration here, right? This is on any pair I can create, but since in the end I annihilate immediately, you will never have this. This is why I showed this example. Okay, so in other words, what happens is that the transition rate from a given configuration to the flipped configuration you can work out is just this thing here. It's the constant mu, because it is deposit independent of what there is, plus w times the sum of occupation numbers. If you think a little bit about it, you'll see this will just be the transition rate from this to that state. Okay, so so generally a transition from any configuration to any other can be written in this form. Let me also observe that the particle parity is conserved, so you always have an even or an odd number of particles, so the system is not strictly ergodic, so this is something to observe. You can have 2 different sectors, and then okay, you just write down your generator like this. So according to what I just described now, I'm working with this generator, and now again, detail in notation, let me point it out. If I work on the torus, I have periodic boundary conditions, and my sum goes from 0 to L minus 1. Okay, I have the nearest neighbor flips on 0 on k and k plus 1. So the term with the L minus 1 has flips on L minus 1 and L, but L is identical to 0 by definition, right? So this is where I get my periodic boundary conditions here in the last term. But when I work in a box, I don't have this guy, the guy with 0. In this case, L minus 1 and L are the last two sides in my box, and so this is why there's one term missing here. The 0 term is missing, right? So it looks the same except for the boundary term, right? That's what I want to point out here. Now, some well-known facts. This process has been studied for decades the way it is. It's easy to show that it's reversible with respect to the Bernoulli product measure with these marginals here. So lambda is this mu plus 2 times w, right? It's this object here, this rate, this effective rate. And the particle density we can compute from this, just expectation of the local particle number. It's given by this one, and you can see this is by definition or by construction always less than a half. I will consider also, let me add that it's also more than 0, because I will assume that mu will always be more than 0, right? So it's strictly between 0 and 1/2. The particle density in this invariant measure. And as I say, it is almost unique. It is not unique because we have an even and odd sector. So if you just look at two projections, you get these two now really unique invariant measures. It's easy to show the process is ergodic, so there will be no question about more than these two measures. Okay, so these are just some basic facts. Now let me introduce another system which is completely trivial. So don't be confused by this. It's the most trivial system that exists. Namely, you just have two states, and you can just flip between the two states, right? That's all that I'm doing here. But let me give it a name to give some intuition. I imagine I have an atom that can be in two levels. One level I call 0, which is the ground state. I call it ground state. The other level, denoted by 1, I call it excited state. Okay, so in other words, the two transitions that can occur in such a system, an excitation is the transition from 0 to 1, and I call it rate mu r, and then I can what I call emission, the reverse transition, which I give it a rate lambda r. Now, and I have not only one atom, I have actually several atoms which are completely independent of each other, right? So it's just a collection of independent two-state processes. Nothing can be more trivial than this. But each one of them, the rates for these these atoms can be different. That's why I have this index r here, right? Okay, so in other words, what I've written here is just writing down again the transition rate. And then a generator is just a sum of generators. As I say, please don't be confused. It's really the most trivial process that you can imagine. And of course, since these are independent processes, it will also be invariant with respect to a Bernoulli product measure, because independent in this case, and the Bernoulli product will have densities which look a bit similar like the previous one, but except of a square root, you have the actual mu, and as we were here, right? So this is just this process, okay? Okay, so it's just a coin flipping, with not symmetric, with different rates for the two biased coin. Okay, so now this is the process described in the usual way. In order to treat this process, I will not use the generator, but I will use the intensity matrix. So basically, it's just the matrix elements of the generator. So defined as follows. The only thing that's a bit unconventional here is that I choose two things. A, define my object with a minus sign. Okay, so usually intensity matrix would have an opposite sign here. And also, most of the literature you will find actually the transpose of this object to be the intensity matrix. But okay, these are trivial operations, it doesn't matter, right? The reason why I choose this convention here is that this makes a link to object known from quantum mechanics, namely it will be the quantum Hamiltonian of a certain quantum spin chain. And this is, then you can use technology from quantum spin systems to treat this intensity matrix. That's the reason why I use this notation, because then one can really go to literature and take results known from the literature and immediately translate. Okay, so again, so the off-diagonals of the intensity matrix are the transition rates from, in this case, eta prime to eta. Here I choose the opposite one and with a negative sign, and then these are the diagonal elements. Okay, so this is just, just a way of writing it. Now, if I work with a matrix rather than with probabilities and transition rates, then a measure simply is represented by a vector. Now in my notation, because I've used this transpose, it will be a column vector that I denote by this. So this will be such some measure P. So it will have the probabilities of configuration eta as components, right? That's what that thing means. And I will also use a diagonal probability matrix, which is a diagonal matrix, not a vector, but just a matrix in that space with the probabilities on the diagonal. These are two objects that will be useful. Okay, then the invariant measure simply satisfies this property. This is just invariance. It just means that under the semigroup it will not change. Semigroup will be generated by exponential minus h t, and then this is the invariance condition. And the reversed process, by definition, so is just by making this transformation on your intensity matrix, on your generator. Okay, and then, okay, at this point I haven't specified at the basis, right? I can put these etas in any order that I want. Nothing of this will be true, but it will be very useful to use a specific ordering of our states, which basically is this lexicographic ordering. It's defined in this way. So if I enumerate my basis vectors, then I look at the occupation numbers, and this will be just the number in my enumerating my canonical basis in this particular fashion. So that means in this case, if all etas are equal to 0, you see this will be just basis vector number 1, and then I just calculate others. So this is my basis, and just some more notation. The basis vector that has the 1 at the first component, which corresponds to all eta k's equal to 0, I will call 0, and then 1 will be this one, and so on and so forth. The point of using this particular ordering is that if you have a general configuration eta, it will be just a Kronecker product of vectors, of two component vectors, so it's very easy to work with this. That's the reason why I'm choosing this basis. Okay, right. Now this is my process, my two processes that I want to consider. The next concept I have to remind you of is duality. Duality is usually defined as follows. Just take two Markov processes with countable state spaces, and then you say that these two processes are dual to each other with respect to a duality function if this relation holds. Namely, the expectation of this duality function of x and omega t starting for omega is equal to the expectation of the same duality function, but now x taken at time t starting from x. So this is the usual concept of duality. Now, why is it useful? Well, maybe, you see, it gives you relation between expectations for two different processes. And it may be the case that one process is easier to understand than the other. Then you look at this process and you get information about the other one, right? That's the idea of using duality. Now, if you write all this in matrix form, then the equivalent statement is the following. You define your duality matrix, so you take your duality function and you choose as a matrix just this basis or generate by this Kronecker products, then you get this matrix, and then this statement here for a countable state space is equivalent to this relation here. So H is the generator for this process for one of them, doesn't matter which way around. G is the generator of the other one, I take the transpose, and then this matrix times H is equal to G transpose times D. This is, you can work out, is the same statement as this one for countable statement. So now there is, so this is the use, and you can perhaps see that this has to do something with symmetries. I will explain it on the next slide, why. The point is that if G and H generate the same process, then you call it self-duality, because, okay, it's duality of a process with itself, but nevertheless it can be useful. And this self-duality has to do with symmetries. This was something that we realized many years ago and which was later formalized in a nice paper by Jardinat and collaborators. Generally, the following is true. Imagine you have, you have an intensity matrix, and let's say this is the reversed process. Then let me assume that there's such a matrix here, S, such that this holds. Then just means that H is self-dual with the duality function given by this object here, right, by this matrix S. So assume there is such a matrix such that this holds, and then I will know there is a self-duality with this duality matrix. Okay, this you can just prove. It's just don't want to go through it. Just want to show it's extremely easy to prove this. You just use this diagonal matrix, use the definition of the reversed, and then this is what comes out. Now, the point is the following. Imagine H is reversible. then H reversible is the same as H. And then you have a self-duality if this relation holds, but that means that you have a symmetry. There is something that commutes with the generator. So there's something that doesn't change over time. And that's a very useful property. For instance, for symmetric exclusion has been used a lot and for many, many other processes. So this is what we are going to discuss. We will discuss a duality and also self-duality for our process here. Okay, so what are the results? Okay, so just some conventions. So here are some matrices. Again, you don't have to remember them, just want to remind them that these are so-called Pauli matrices enumerated in this way. Then I build certain linear combinations out of these guys, and I use sigma 0 as the two-dimensional unit matrix and the boldface 1 for the generic unit matrix in any dimension. Okay, so this notation. Then you can, okay, some more notation. So this would be two-dimensional matrices, but then I work on my big vector space with L sides, and then I have to define Kronecker products. So a matrix that has a subindex K is a 2 by 2 matrix that acts in a non-trivial fashion only on oh, there should be a K minus 1. Apologize for the typo. So it should be K minus 1. So on the first K minus 1 sides, it doesn't change anything. On and side K in my chain, it does something, right? That's what this thing means. And the remaining sides, it doesn't do anything either. Oh, no, sorry, this is counting from 0. That's why there's a K here. Okay, fine. Okay, good. So then if I have a double index, it means I have a 4 by 4 matrix acting on two neighboring sides. And then I have to define here what happens at the boundary. Just, okay, just again, it acts in a non-trivial fashion across the boundary, which is, in the case of the torus, just a ring. Okay, so now some more notation here. This symbol here means the commutator AB minus BA. This means the anticommutator AB plus BA for any two matrices. And this guy here is a Q deformation of the matrix A, which is defined via the exponential of the matrix in this fashion. So now let me introduce a more complicated object, and that's a so-called quantum superalgebra. Well, really, it doesn't matter too much what a superalgebra is nor quantum algebra, but these are objects that play a big role in quantum mechanics, in integrable system and quantum spin chains. Let me just give you what is the definition. So you have an algebra, right? Algebra has generators, and this generator satisfies certain relations. That's what defines an algebra. Now, what it boils down to is that I have an algebra with 4 generators, T0, T1, T2, T3, and they're subject to these relations. So this would be anticommutator of these two guys gives 2 times the Q deformation of T0 and so on and so forth. Now, this is an algebra, and for reasons I don't want to get into is called a quantum algebra because of this deformation here, and the superalgebra because it has both commutators and anticommutators. Again, just doesn't really play a big role. The use of this is that these are well-known objects, and I can use technology from algebra to treat these guys. Okay, and then by looking at these generators, at this relation, you can see that the subalgebra, if you just kick out T3, you will still get a closed algebra, so you will never kind of generate T3 if you just look at these relations here. So this is subalgebra, and this I will call the Hinrichsen-Rittenberg algebra because these two guys were the first in 92 to consider this algebra. Just a remark. One remark perhaps, if I replace all the anticommutators by commutators, then it's not a superalgebra but an algebra, and this is a Q-deformed universal enveloping algebra of the Lie algebra GL2C. So that's why this is not such a strange object as it might look. Okay, now some more stuff I need to introduce. Again, all this comes from quantum mechanics, from the treatment of quantum spin chains. There's something that's called Jordan-Wigner transformation. So you introduce objects which are basically these spin operators, these sigma, these Pauli matrices, but you multiply them, the 1 and 2, you multiply with a string of sigma 3s. So you start your lattice at side 1 or side 0, depending on exactly which lattice we're working on. Here in this case, I will mostly use, at this point, I will talk about the box. Okay, these are definitions. And then it turns out that they satisfy these anti-commutation relations. And it has been shown by Hinrichsen and Rittenberg that you get a representation of this subalgebra by defining objects like this. Okay, this is something they could prove. Okay, so this you can ignore. It's not important now. Okay, so now, okay. The point is that this algebra is a symmetry algebra of my generator. And therefore, I can use this general theorem that I mentioned to get a self-duality. And what happens is the following. You take this duality matrix, which is just composed of these generators, C1, C2, and the product of them. And then what I'm saying is that the process is self-dual with respect to this duality matrix. And not only this, it's also the most general duality matrix that arises just by using the supersymmetry. You can invent other dualities, but if you just want to make use of the supersymmetry alone and nothing else, then this is the most general duality matrix. Now, what does it mean in practice? It means that the even and the odd sectors of this process are dual to each other with respect to this duality matrix, with these two guys are zero. This is just a corollary. So that means if you have a process with an even number of particles, you can compute basically everything you want if the number of particles is odd, and vice versa. So that's basically what that means. Now this works if you're in a box, right? Now if you're on a torus, then this supersymmetry doesn't hold anymore, and also the statement will not be true anymore. But there's one more property here, which I will come to a bit later, which is called integrability, and this will work also on the torus. Okay, so let's go then continue, and let's look at these results from integrability. Again, I have to introduce some more notation. Again, you don't have to remember it, you just have to some idea what these things are. Basically, I introduce a variable phi plus minus, which can be 0 or 1. And then I look at these tangents, cosine, and sine functions. Basically, it's just an angle, sine and cosine of an angle of a discretized angle on the torus. Okay, now let me look at independent atoms. There is a slight problem with integer and with even and odd n is a technical problem. So let me just look at even and odd system size separately. So if I have an even, so if I take L, okay, if I take L even, then this m plus will be just L over 2. But it depends, whatever. I take two different types of sets of independent atoms, where the number of independent atoms is just a function of the original size of my lattice of the DAP. And I define my rates, remember these were the flip rates of my independent atoms, to be these objects, 2 times mu and 2 times lambda. These are the original rates of my DAP times these cosine functions, which I've just defined here. So this is just a definition. Okay. Then, yeah, this one actually I don't need now. Let me just look at the lower definition. Let me remind you again, object from quantum mechanics here, which is a Slater determinant. Slater determinant is the following thing. You take a number on the unit circle, so exponential I alpha, something like this, right? And you basically, what you do is you take exponential okay, so you take exponential ki times alpha, it will be on the unit circle, you raise it to the power p, and you write this determinant. Then this thing is called a Slater determinant, okay, for plane waves. Just again take it as a definition. Now the result is the following. I define this duality function here. Again, a duality between two processes. K is my process, the DAP, where I enumerate my states according to the number of occupied sites. So I do not look at the occupation number 0, 1, but I say which sites are occupied. And I call this set of occupied sites, I call K. R just tells me which atoms I look at. So just a set of atoms. So, and I'm saying that my process of the independent atoms is dual to the DAP with this duality function here. And this would be true for the even sector, and the similar statement would be true for the odd sector. Okay, so again, this is just a duality. What it is useful for, I will show you later. But it's not such a trivial duality as the previous one. The previous one was done by generators of your superalgebra. Now on the torus, I don't have the superalgebra anymore, but I do have these plane waves from which I can build the Slater determinant, these exponentials of the unit circle, and then I can find a duality between my interacting process, which is the DAP, where particles jump and annihilate and can be created, with a system with labeled by K, exactly. Precisely, exactly. So there's duality between the interacting system and the collection of independent particles, non-interacting. So that's why this is potentially useful. So I have an interacting system and it's dual to a non-interacting system. And non-interacting systems, particularly if we have only two states, are of course trivial to treat. So we can, with trivial manipulations, we can obtain interesting information about this interacting system. That's the point here. Now, this is just a remark here, which okay, I don't want to go into. What can we use it for, this duality? Many things. I give you 2 or 3 results here. So first of all, let me look at the following object, for which you can use duality to say something. Let me count number of particle jumps in my DAP. So I count the number of the first model, right? Yes, exactly. So my particles jump on the lattice. I started in some initial configuration and I count how many times a particle has jumped to the right. So K is the number of jumps from K to K plus 1, and J minus K would be the number of jumps from K to K minus 1, right? So, and I count them up to time T in my process. And the difference of the two and the sum over all of them, I just call the integrated current. Why is it the current? Well, you count the number of jumps to the right, number of jumps to the left. The difference, of course, will be a net flux of particles. And I take the average over the whole lattice, so I go over the whole lattice, right? And integrate it because I count all jumps up to time t. This is a random variable. And I also look at this scaled random variable. I take the same object, but I divide by square root of L and square root of t, right? It's basically the same object rescaled. Okay, a random variable you can study. You can look at the generating function, which will be just the exponential of s times j. And of course, well, you can look at the corresponding one of the scaled guy. And trivially, these two functions are related in this particular fashion here, right? Obviously, because just the scaling factor. Okay, from the generating function, you can compute other properties like the cumulant generating function. You take the log of this guy, right? And corresponding the log here. And with this, you know a lot about the random function, about your random number at time t. Basically everything you know about at time t. Okay, so now what can we say? Well, okay. So let me first define the asymptotic cumulant function. So I take my cumulant generating function that I just defined. It's a function of s, which is just the conjugate variable, exponential s times j, right? And this time t. Now let me divide this guy by t. Why? Because, well, the number of jumps for sure will somehow increase in time in a linear fashion, right? If you have some imbalance, this is what you will expect. So I divide by t, and I take the limit where t equals to infinity, but still keep L finite. But then I also want to look at the infinite volume limit. So again, if I make my system bigger and bigger, then of course I expect this number of jumps to grow linearly. So I take this scaling here and look at this limit. This will be well defined, as you can see, and you can see that the integrated current has this functional form. So it's actually quite simple. So it's a square root of cosines, of cosine squared and cosine. And okay, then you take this integral. You have to subtract something and you take this integral. Now, this limit we find is independent of the initial density and also independent on whether or not you have an even or non-odd number of particles. This is not very surprising. Basically, it follows from this supersymmetry that I mentioned in the first case, because this will not play any role, but also intuitively you can imagine the difference between even and an odd sector in an infinite system is, of course, will somehow disappear, right? But anyway, it can be shown using the duality. The first one that I mentioned, if you are in a box, you take this limit, it will not matter. Okay, so now, okay, this is this guy here. There's an explicit expression that we have for this as a function of this factor. And so And if you look, so first of all, what you see here, this is not, it's a cumulant function, generating function, so it will have non-trivial cumulants. So that means it will not be a simple Gaussian distribution, this random variable, right? It will be something more complicated. However, if I look at the rescaled one, right, then I put in here my s over square root of lt, and that here at this point, and then I take the limits, and then I get something much simpler, and then we see that it's actually a normal, that this rescaled actually has a normal distribution with this variance here. And this is just a stationary density of the process. So on this scale, you get a normal distribution, but if you look on a finer scale, you see actually that there are fluctuations around this, which you can express in this particular fashion. Yep, okay, right. Yes, it's here. So you take your generating, this log of the generating function. Okay, generating function is the expectation of the exponential of the random variable, and the log is the cumulant. This gives you the cumulants. So if you expand this in S, okay, S equal to 0 gives 0, because it's put in S equal to 0, it gives a 1, and the log of 1 is 0. The first derivative gives you the exponential of the current itself. S squared gives you the variance, and then the higher cumulants are, well, defined as they are. This will just give you, so an expansion in S gives you all the cumulants. So basically what I'm saying here is the following. If you made an expansion in S, this will have a non-trivial third cumulant, this guy here. It will not vanish. But if you look at this scaling, where you scale the random variable by square root of LT first, you will get just a normal distribution. It's a bit funny, but it really means that you're looking here at in a more precise limit than in this one. Okay, so now how can we explain this difference between the scaled one, where you scale out these corrections, and the more precise one? Well, there must be some kind of correlations that lead to the difference between, a Gaussian would expect for independent variables. So the fact that you get, for the scaled one, you get a normal distribution means that any correlation between these guys do not play any role. But if you look more precisely, you see that there are some correlations that change it. And okay, so that's the first thing that we see. The second one is just a remark, because you see, you may wonder why this guy is 0 at density 1/2. Why would variance be 0 at 1/2? Well, to remind you, density 1/2 means in the original process that there are no particles at all. So that means that this is a trivial case limit. This is not something to worry about and not something to consider. And then let me remark, and this I will come to in a moment, here we looked at the current, which is the difference of particle number jumps. We can also look at the sum of the two, which would be the total number of jumps, and this will come to in a second. You can obtain it in the same way. And as I say, all this follows from this duality that I mentioned, as I will explain in a moment, but let me just continue presenting results. Okay, so now I've given you the expression for the current. Let me now look at the activity, but what I'm going to say here will be essentially the same in essence. Let me now look at the sum of the two guys. Let me call this the activity, right? Same object as before. And let me now look straight away at this scaled one and see what it behaves like. Well, actually, I look at this one first, and then I will study this later. So I have same definitions, right? I get a generating function, I get a cumulant generating function, and now I really want to know a bit more about this correlation that I have in the system. So let me define what is the dynamic structure function, which will tell me how my occupation variables at time t at side k are correlated with those at time 0, at side 0, in my invariant measure. Okay. So this is just this thing. If I can compute this, I will be able to say something about correlations. Now, one thing I can tell straight away without proof, yeah, over the invariant measure. Yep. Right. So that's this object here. Well, it's the invariant measure of this variable at time t. Yeah. Okay, eta k times t multiplied with eta 0 at time 0. This product is a random variable, right? And I take the expectation with the invariant measure. That means that this whole thing will depend only the difference of times between the two. You see, I could compute this at t, at this t prime, But if I take an expression of the invariant measure, will depend only on t minus t prime, and then I can t prime to be 0, right? That's why I have a 0 here. Basically, it tells you, you can give it a different interpretation. You start your system invariant measure. You condition it on having a particle inside 0, because you multiply invariant measure with eta 0, right? And then you see how this measure evolves in time, and you measure the expectation inside k time t, right? This would be the same thing. Yes, right. Yeah, right. Yes, that's, yeah, it's one way of seeing it. Yes, exactly. Right. Yep. Yep. Okay. So now, okay. Now, okay. Now let me say something. Okay. Now, what can I say about this? Well, this process has been studied a lot, I told you already, and I can tell you straight away that if you look at this function, this will decay exponentially in time, and we're talking about microscopic time, right? So this will go down like exponential times a constant times t. So if I do all this rescaling and I look at large times, this will essentially quickly decay to 0. This will become uncorrelated very soon. And this is the kind of explanation as to why the rescaled current and also rescaled activity will have this property, will have normal distribution. Okay, so this explains this difference, because it's known that this guy decays fast. However, there is something funny, and let me explain the following. This is if I just let my process run and look what happens. However, what you can do something different. Instead of just letting your process run and look at anything that happens and then take an average, you can condition your process on something not typical. So you can, for instance, condition on your process on having a certain number of jumps, right? So you look at your process, you let it evolve in time. If this doesn't have this, if it didn't have this certain number of jumps that you specify, you just forget about it. You let it run again. And then you wait until you have a process where this number of jumps has been realized, and you keep it. You look. Then you do it again. You do it again. Whenever your process has a certain number of jumps, you keep it, and then you compute an expectation with respect to that measure that you obtain by conditioning on a certain number of jumps, right? So this is what I call a conditioned dynamics. Now, this conditioned dynamics, again, can be described. This is a technical point I don't want to go into here because it's somewhat longer. It's large deviation theory, by looking at this generating function here. So this is just, I just want you to believe you use large deviation theory to compute this conditional expectation. Now what comes is the following. You condition your process. Okay, I do not take a fixed number of jumps. I take the conjugate quantity, which would be just the Legendre transform of this number of jumps, and the parameter for the Legendre transform is my S, right? And that appears in this generating function. Again, it's a result from large deviation theory, so just believe it. So now let me just define the following functions. I define the function h of s being the rate of jump divided by the creation rate plus rate of jump times exponential s, and I find this function eta of s, which would be just minus h squared times the exponential of 2s. Now, as I say, this s here is my conditioning parameter. If I take s equal to 0, then it means I just let my process run without any conditioning. If I take a positive s, then I look at a process that has a higher number of jumps than typical. If I take s to be negative, it will have a lower number of jumps as it would typically have. So that's the interpretation of this s. You can compute exactly the relationship between the two, but it's not important. Point is, if I make this conditioning, then the invariant measure under this conditioning will not be your original invariant measure, because you condition on something atypical, and then there's no reason why this invariant measure of this condition should be the same. In fact, it's not. It will have a density, which is not just what I wrote previously, but will have a density that's given by this integral. It will always be less than a half, as it has to be, right? It cannot be more than a half. But how much you subtract is, okay, not very difficult, but not trivial function of s. Okay, this is something that, again, you can compute using in the same fashion as I had done before using duality, but in actual fact it had been computed by different means already a long time ago, in the 60s already, from this mapping to quantum spin chains. So now you can also use this Slater determinant that I showed you before to show that the dynamic structure function, this correlation function, has the following universal scaling form. So I take k, my lattice value, I take to be I make it very large. So I take okay, let me write down here. Yeah, S is the Legendre transform of my conditioned. So I condition number of particles, and then I take the Legendre transform of this ensemble, and S will be parametrizing this. It's like it's the large deviation function will be the rate function, and it's the parameter that appears in the large deviation function. So if you take a large deviation function, it will be exponential of some constant times your the quantity that you want to look at, and this okay. So yeah, okay. So I look at S times A, right, of t, right. This gives me, this will be proportional to some function f of s, right. This is my rate function times times t, right. So it's this parameter here that I'm talking about. That in basically this. Okay, let me show you this guy here. This will be the rate function, this guy. Yeah, for the current, right? Now I do the same for the activity, and it will turns out that it has exactly the same form, except that this f of s is not 1 minus cosh, but it's 1 minus exponential s. But this will be the rate function, this thing here. Okay. And from this rate function, I can compute the expectation of the density, and it happens to be this in the limit. So that's how it works. So that's how this expectation density will be a function of that parameter. Okay, it's this one. Good. So this is, when I look at the dynamic structure function, I need to know what this thing is because I have to subtract it. Remember, the structure function is this expectation of eta times eta k of 0 at time t times eta 0 of 0 in the invariant measure. So I have to know the invariant measure and have to subtract the rho squared, so I have to compute this quantity. So, and then I look at the structure function, and if I rescale it, so I take my lattice coordinate to be proportional to t, and take the limit where t goes to infinity, and then I find that this is going to be a function of x only, here, right? And it's this function. So that means that this scaling function is actually it is something that we call universal, because the same function will appear in other models as well. And also, you can see it doesn't disappear, provided that h, this parameter, is equal to 1. So there is a particular value of my parameters of the model where h is equal to 1, and if and only if h is equal to 1, I will get something that does not simply disappear, even if it takes time to infinity. Right? Remember, without conditioning, this will decay on microscopic timescale very fast, but here it doesn't. So that means also that that indeed there are correlations, and they can actually lead to a quite drastic change of behavior in my large deviation properties. That's basically what we are saying here. In fact, it is a phase transition, because you can compute derivatives of this function with respect to h at h equal to 1, and you will find that it will diverge. So so this is again something known, d rho star dh. This will tend to infinity at h equal to 1. And this is indeed the signature of a second order phase transition in quantum systems. And so that means there is a radical change by going from subcritical activity to supercritical activity at the critical value of activity. So imagine h is 0, then my behavior is typical. Now, if I look at a slightly higher number of jumps that would normally occur, the behavior doesn't change in any significant fashion. My distribution of my random variable, of my activity, and of my current will still be a normal distribution. But there will be a critical value if I make my activity, if I given model parameters, if I choose my activity to be a specific value given by this parameter S, there will be a point where my correlations do not decay exponentially but very slowly algebraically, and then I will get big changes in my behavior. Then if I'm supercritical, if I make S even higher, again I will be back to exponential but in a slightly different fashion, but still will get normal variables. So that's basically the story here that we get. So there is a critical activity at which my behavior changes. Yes. Yes. So I look at realizations where I have a certain drift, right? Yes, physically, right? Yes. Yeah, right. Exactly. Well, you see, my system a priori has no bias, right? It's the same. But of course, it can happen by chance that there is more pulse going one way than the other, right? This is for torus, yes. Yeah, right. But I take the limit where the term size goes to infinity. On a finite one, I will not have a phase transition, but only something that looks a little bit like it, but not quite. Yes. Yeah, well, I condition on having that. Right, exactly. Yeah, right. Yeah. So as I say, normally on average it will not appear, but of course you have a random process, everything can happen, right? And so with some small probability you will have this flux, right? And then you just condition on having that. Huh? Sorry? Well, I condition, I condition, well, I condition on this to happen, you see? Mm, okay, look, no. You see, if let's take a coin flip, right? I can condition on having only tails, right? It will happen with small probability, but if I condition it will happen forever simply by condition on it, right? So I can condition on having 50 times, 100 times, a million times only tails in a row, right? Probability will be small, but since I condition it will be there. Of course, you can generate this behavior by manipulating your coin. So you change your pose a little bit, you make one side of the coin heavy, and then of course will always drop on one side, right? It's the same here. If I don't do anything, I just condition my process that there is this flux, right? So as long as I condition it's there simply by defining it, because I just look at those realizations and compute its properties. However, I can manipulate my process in a way that this becomes the typical behavior. It's like making a coin that's not symmetric. And indeed, we have looked at this and computed what you have to do. We have to introduce an interaction between the particles, so they still have nearest neighbor jumps as before, but the rate of jump will depend on your whole configuration, and then this will happen forever. I didn't say this here, but this can actually be done for the current condition. Current we have done it. For the condition activity, in actual fact, we haven't done it. So this is one open question. What exactly is? It will not be the same, I can tell you. Will be kind of similar, but not exactly the same. So it's actually interesting to see what will happen. But anyway, this can be done. So I can look at the process, modified process, but this will be typical. And then you will see this phase transition in this modified process. Okay, so these are the results. So let me then just as I say, the proof is like in the density. So I will briefly explain how it goes in a moment. Then these correlations, you can use it from this later determinant that I've showed you. But as I said, this maps to a long known problem. So we actually don't have to do it. We can just look up in the literature what the correlations are like. So we didn't have to compute that. This is really from 1967, essentially, this result. The point here is that this corresponds to what in quantum physics is known a critical point, this h equal to 1. And therefore, we can expect this to be universal behavior, because at critical points with the second order phase transition, the behavior does not depend on microscopic details of your model. It will be generally true. So other models will have the same behavior, even though we cannot directly prove it. This is what we expect. As you can see, this here, right? This guy is just a Cauchy distribution. right? This 1 over 1 plus x squared. So basically, your covariance of your occupation numbers, this will follow a Cauchy distribution if you take this as a variable here. Okay, so now how do you prove it? Well, this I want to go through quickly because it's very technical. The point is the following: you use this Jordan-Wigner transformation that I showed you. It's here. So instead of using your local jump generators, you express them in terms of these Jordan-Wigner operators, which have anti-commutation relations with different sides. You see, these guys, by definition, by construction, commute on different sides. So whether I compute the product sigma k times sigma k plus the same as taking sigma k plus 1 first and then multiply sigma k, right? This is just a trivial property of the Kronecker product. But these guys here, they anti-commute. If I invert the order, I get a minus sign. That's the way how they're constructed. So that's step number 1. You have to go to the Jordan-Wigner operators. Step number 2 is you have to differentiate between the even and odd sector, right? So this is just a reminder, so you don't have to read this. Third step is you write down your density matrix in density matrix for these independent atoms and use these relations, and then you do the following. So first of all, your generator is not a symmetric matrix, but you can make it symmetric by making this diagonal similarity transformation. This, remember, this is the matrix that has the stationary weights on diagonal. Any reversal process can be, you can make the generator diagonal by this kind of transformation. So then it just becomes like this. Okay, this can be sigma 1 is the sigma x, that is a symmetric matrix, so this is all symmetric. Now, this guy here, this is exactly this quantum Hamiltonian that's known from quantum physics, exactly like this, right? So I can now go to the literature on quantum spin chains and read off many results. So for instance, I can read off this symmetry that it has with this Hinrichsen-Rittenberg algebra. So I know that this guy in a box will commute with these generators of the quantum algebra, and then I know that I have self-duality. So this just follows from this general theorem. So this is how I prove the self-duality. And then the uniqueness comes simply from the fact that I have the superalgebra. That means that any square of these guys will be 0. This comes from the anti-commutation relations. Okay, so that's the way how I prove self-duality. Now, how do I prove the duality with these independent atoms? Well, here some new ideas come in, namely, remember this Jordan-Wigner operators. Well, first of all, let me write them in a Fourier series, discrete Fourier series. Then look at these products of pairs. So I have a B dagger, which is just the complex conjugate transposed, and I construct these guys here. And it so happens that I can express my generator in terms of these objects, B dagger, and these here. So now, okay, now come some technicalities which have to do with representation theory of my guys. I can express my Casimir operator in this fashion, and then the main point is that this my generator can be expressed in terms, as I said, of these operators here. Now these operators here, they satisfy an algebra which is isomorphic to that of the original Pauli matrices. Since the algebra is isomorphic and they have the same Casimir, that means that if I manipulate, if I take exponentials, I may just as well work with these Pauli matrices, but my independent atoms are exactly those Pauli matrices. The generator is expressed in those. And therefore, this is basically the idea where this duality comes from. So again, my generators of the DAP can be written in terms of objects that have the same commutation relations as Pauli matrices. My generator of the independent atoms is written exactly in terms of these Pauli matrices. Since the Casimir is the same, we are working basically in the same representation, at least on a certain subspace of my space, and therefore these two processes are dual. That's the logic of it. So it's an algebraic proof of duality. Okay, so that's really the idea. So here's the more technical part, how you do this. Okay, this, as I say, is just a kind of technical, very technical thing. Now how do I use it to express the current distribution? This will be my last one. Okay, so my definition of integrated current is the expectation of this guy here. So where this is some tilted generator, again this large deviation theory. Now I use my duality to express this generator of my independent atoms, and of course for independent atoms everything can be computed trivially, and that's where this expression comes from. So that's basically it. So that's how the proof works. These are the main ideas. Everything else, as you can see from the slides, is very technical, takes a long time to explain, but of course you can read it. Thank you.
Thank you, Gunter. Do you have questions? You want to make some questions? People is not listening to. I would like to know a little bit about the condition you have to put in your rates.
Okay.
If you want this rate which depends on your whole system in order to have some different kind of flow in your result.
Okay, yes.
Which is the condition you have to put in your system actually.
Okay, right. Okay, we have done this in a specific case, namely where you send this S to infinity. Sorry. So it shows you something that will be generic, but it can be computed explicitly on this limit. So first of all, what does it mean? It means that we look at the maximal possible activity. Or current in this case, or current. Let me work out the current. This is a bit more intuitive. Now, what does it mean we take S to infinity? Well, we take the maximal current that can possibly happen. Now, under which condition does the maximal current occur? Well, only if particles only jump to the right. This is the way how the current can be maximized. So basically, we are looking at a process where particle jumps happen only to the right. So this is something you can say without even any making computation, if you look at this limit. But then, as I say, this is not sufficient. Just making, so you could imagine you just take the asymmetric part of your generator, but this will not generate this process, this conditioned process. What you have to do is a dope transformation. So this is something. Okay, again, a technicality to get really something for which this here arises as the typical behavior. You have to look at this limit in an appropriate way, and then you can compute explicitly the generator of the new process. Now, how do you do it? But just to tell you what it looks like in general, you have your matrix here, your generator here, your intensity matrix, and you have to make a transformation of this with a diagonal transformation. Oh, sorry, you probably cannot see this here. So you make a diagonal transformation delta minus 1 with the diagonal matrix, and the diagonal matrix that appears here is the left eigenvector of this guy at the value of S. Now this is this dupe transformation. And you have to subtract the lowest eigenvalue E0, and then you can show that this guy here again will be the intensity matrix of a new process. So now, okay, so this is something that you can formally write down. Explicit computation is possible if you make the technical limit where S go to infinity. What comes out is what you expect, namely that this guy will have only jumps to the right, this transformation, but the jumps to the right, they will depend on the whole configuration in a particular fashion, and we can compute explicitly what it looks like, and it is a long-range interaction. So it will go down, so there will be something like a product, so the rate of jump of a particle to the next, let's say, okay, we have a particle jump here from k to k plus 1, and then the rate, this will be proportional to 1 over basically the Slater determinant of all the coordinates. So it will be in a certain ways. It will look like this: a product, a double product, sine ki times kj times some pi over p pi over l. So and it's the inverse of this. So it is no, sorry, this will be the distance between these two particles, right? So it will be rj. So if you think of small distances, this would be like a inverse square interaction. So the rate of jump will decay quadratically in the, okay, there will be sine squared here, in the distance of all distance that you can have. So this, just to tell you, we can compute explicitly what this interaction is like. It will depend on the whole configuration in a long-range fashion. Yes, this quantum XY chain, this is an example, right? This is a spin system, a quantum spin system, where you have a chain of spin 1/2. So you have atoms with spin 1/2. So the sigma one can be plus minus 1/2, and they have the interaction. This is this sigma xi, sigma I plus 1 x plus sigma I y, sigma I plus 1 y, plus h times sigma I z. So this is a quantum system where you have a spin exchange interaction between neighboring sites and an external magnetic field, and this has exactly this phase transition at h equal to 1. It's quantum. Okay, and you mean a classical? Okay. Okay. Well, as I say, the classical system that will have this property is this transformed one, which is the same jumps but with these rates, or rates that are similar. They will have exactly this. Well, it is. Huh? Sorry? It's a model, right? Yes. Well, this is physical. No, it is. I mean, this is not. You see, this maybe it looks artificial to you, but it's not. In actual fact, this interaction here is actually appears in the so-called Calogero-Moser models, which again are quantum systems, but nevertheless, this is just a classic analog of a Calogero-Moser model. So it's not so obscure as it may look. Look, it gives you a practical application. Imagine traffic flow between cars, right? You know, if the density becomes very high, you get traffic jams, which you don't want, right? You know it very well on the marginal here, right? So it's something that you want to avoid if possible, right? So now the traffic flow is a particle system, right? Parts interact in some particular fashion, and the flux of particle will depend on the density, right? And will depend in the density in a monotone fashion. This empirical goes more or less like this. So if density becomes too high, the flux goes down very, very quickly, right? Okay, so now how can you prevent such a situation from happening? Well, the cars have to interact in a different fashion, right? If car drivers behave not as they behave in reality, but you force them to behave in a different fashion, then maybe you can avoid these traffic jams. And basically what it's telling you here is the following. Take your process at this density, condition it on the rare event that the flux is actually okay at this density. This can happen, right? Now you make this transformation, you compute which interaction you need in order to make this atypical behavior typical. If you enforce this onto the cars, they will behave in a nice fashion. Now, technically, it is not easy to, technically it's actually easy. You see, you have GPS. GPS measures the positions of each and every car. It measures the velocity. So it can actually compute how the driver should behave as a function of the driver that he sees ahead and the other drivers. It could tell him, do this, accelerate, slow down. So technically, it's actually not so difficult. Whether people will follow the suggestion is a different question.
Okay, I'm afraid that we are out of time. Okay, quick and knife question.
What type of fitted graphs that you can consider this besides this? Does it make sense in, say, complete graph?
Okay, in a complete graph, these techniques will not work because we really use the linear structure. When you make this Jordan-Wigner transformation, this will work only on a linear chain. Because it has this particular property of having to have only one defined neighbor. You can't have more than one neighbor, and it has to be linear, right? Okay. Otherwise, it will not work.
But the questions, they still make sense in complete graph, or?
The question, yes, but the answer will be different. Okay. Thank you. And a complete graph, I think, will be even harder to generate a phase transition because behaves. Yeah. Right. Yeah.
So he answered it. Yeah. So thank you, Gunter. I think we have no time anymore. So let's thank Gunter.
Okay.